Because, you know, we have a basic graph class, right? We gave you a graph library. And on the assignment 7, you're going to use this library. You're going to write these functions like depth first search and Dijkstra's algorithm and A star. And those functions all pass in parameters to you that are the starting and ending vertex and this graph that they come from. And you have to find the path, return it as a vector of vertexes. So we're going to use this library in assignment 7, so you don't have to write the graph itself from scratch, only the algorithms to search it, right? And also the algorithm to do the minimum spanning tree on it. But I do think it raises the question of, like, how does this thing work? I mean, somebody designed this and built this and put these methods in it. So how do you implement a graph class? Well, I think you could just invent a way of implementing it. I mean, some people have thought this over and come up with some good ways. I'm going to share those with you now. But the main things, whenever you're implementing any kind of data structure, you just want to ask yourself similar kind of questions, like what operations should it support, and how efficient can I make those operations? What representation can I use that will make these things run well, make them fast, right? So you would kind of look back on these methods here or something similar to this and say, if they want to do these things, how do I do that? So there are 3 ways you can implement a graph, and I'll just show you them quickly today. And I guess what I would say is that I will not directly test you on being able to implement a graph these ways. But this is understanding that goes into the algorithms that we're going to do on our assignment. So one way of implementing a graph is called an edge list, which is that internally the storage of what you keep about the graph is just you keep a vector or an array that stores all the edges. So like if the graph has these vertexes in it, I guess this is an undirected graph, then you would just store there's an edge from 1 to 2, and there's an edge from 1 to 4, and there's an edge from 1 to 7, and from 2 to 3, and then so on. And that's all the graph is internally. And you implement all of the various operations using that one and only structure as your backing data. Okay? What do you think that this representation is fast at or good at versus what is it slow at or bad at? Like, what's something this representation is good for or can do well? Or like I said, what's something it doesn't do very well? If you ask the graph, hey, tell me this about yourself, and the graph goes, that's going to take me a while to figure that out. Yes, sir?
You want to check if the edge is in the graph.
If you just want to look for an edge, like, is there an edge between these two? So how would you answer that question? I guess if this was like a set of edges, you could ask if it were a member of that. If this were just a vector of edges, you might have to loop over it and look for the edge. So depending exactly what sort of structure that is, it might be fast for answering that. It might be slow. I think it definitely would be fast for, like, I want to print out all the edges or loop over all of the edges. They're all just sitting right there stored in a collection. So that would be pretty good for this representation to do. Can you think of any other stuff that it's not very good at? What is it bad at? Yeah. Yeah, tell me all the neighbors of vertex number 4. In order to find that, you'd have to like loop around in here and look for all the edges that have a 4 in them somewhere, right? You could probably imagine ways to tweak this that would make it less slow for that, but I'm talking about just this. This way, this thing would be slow for that question, right? Give me all the neighbors of a given vertex. It's got a Socrative logo here, but I'm going to spare you. I'm going to just pop this up and say these are some of the kind of operations you do on a graph. I'm just asking you as a group, just somebody kind of raise your hand and help me out here. Like, so it's, let me see, what's the answer to this question then? Which operations are efficient? You said finding if an edge exists. You mentioned that before, from A to B. Looping, iterating over all the edges, pretty good. Looping over all the neighbors of a vertex, you just said that one's really bad, really slow, right? Finding out the degree of a vertex, how many edges touch it, that's kind of like what you said is the same sort of thing. That one's going to be really slow too, right? Anyway, this representation it has some flaws to it, right? I think there are other ones that we might want to look into. So another one that you could use to represent a graph is called an adjacency list. An adjacency list is where you have basically an array representing all the vertexes or a linked list or something like that. And for each vertex, you have a list of its neighbors. I've drawn it as though it were like a linked list with pointers, and it could be. But it could just be that these are vectors, a vector of vectors or something like that. And what you're doing is if you want to know about vertex number 5, then you go to index or key number 5 here in this structure, and then all the ones that it's connected to are stored as neighbors here in this thing, right? So what's good and bad about this representation? Yep.
To return a list of edges, you have to loop through everything, so that would be slow. But
So if you want all the edges in the whole graph, yeah, you have to like walk this entire thing and put it all back together and say, here's your list of all the edges. Yeah, so it almost has an opposite set of pros and cons to the edge list, right? What is it really good for? Or is there anything else that you want to say that it's bad for? Yes?
This seems to be pretty much custom built to answer the question, what are the neighbors of vertex such and such?
Yeah, this is a really good representation to find the neighbors of a vertex, loop over them, print them, visit them. Some of our algorithms we have to code involve visiting all the neighbors of the vertex, right? This representation might be good for that. You don't need to worry about that because you're not implementing the graph from scratch. You're using the basic graph. But hey, maybe the basic graph, if it were implemented this way, maybe it would be efficient for our algorithms that we have to write for homework 7. Yeah, that's basically the target of this representation is it's fast for looking for the neighbors, right? Is it fast or is it slow to answer the question of like, are these two vertexes neighbors of each other? Rather than give me all the neighbors, I want to know just about these two vertexes. Is there an edge between them? Is this fast or slow for that question? Yeah.
Again, I think it's quick because all you have to do technically to know if one is connected to the other, just check the neighbors of that one, see if the other's contained in it. If it's not, check the neighbors of the others, see if it's contained in those.
Right, just basically similar thing. If you want to know, is 5 a neighbor of 7? You just look at the neighbor list for 5 and see if 7 is in there. So you have to like loop through that if it's literally represented this way. But maybe the assumption is that these lists are not that long. Maybe every vertex doesn't have that many neighbors, and so that's not going to take that long. So it's not like just instantaneous to answer that question, but it's pretty fast. I certainly don't need to go looking at all the graph to answer that question like I would have with the edge list, right? So this is pretty fast for answering are vertexes I and j neighbors of each other. But it's not like immediate answer, right? It has something to do with like big O of average degree of a vertex, which is probably related to the number of edges or something like that. OK, right. So that's what it's good and bad at. So we just sort of talked about this. I'm not going to sit on this slide very long. There's a third way that you can represent a graph. And that's called where? Wow, I had a lot of slides on it. I'll come back to that in a second. Another way you can do it is called an adjacency matrix. An adjacency matrix is a little bit like an adjacency list, except instead of having these differently linked lists at each vertex, you just make a two-dimensional grid or two-dimensional array. And the idea is that the row and column, like if you go to row 5, column 7, that's asking, is there an edge from 5 to 7? That's what that's telling you. It's like a grid of Boolean data. I could have written true and false here, I guess, right? Basically Boolean information. And so this one, I hope it's clear, this one is custom made to answer one particular question also, which is like, are these two vertexes neighbors of each other? Really fast for that. Even a little bit faster. I mean, you said that the previous one, the adjacency list, was not very slow for answering that same question, which is true. This one is even faster than that, because I just jumped to the right place in the grid. It's got a 1. Yes, they're neighbors. I'm done. I don't have to loop. I don't have to look at anything else. Boom, I'm done. If you assume it takes a constant amount of time to jump somewhere in a grid, which it does, generally speaking, then this is even faster for that one operation. Yeah.
If you were building the what was the other one called? The one
adjacency list.
Adjacency list, and the list of neighbors for each vertex was something like a hash set. That would still be O of 1, would it not?
You're saying that instead of having, if I made an adjacency list, but instead of using like a linked list or a vector, if I made this like a hash set, then this one would also look up the neighbors really quickly.
It would again be O1.
And that's pretty much what the basic graph does. It's an adjacency list with more of a hash or tree-based list set thingy here. So the lookup is a little faster. And so it tries to kind of get the best of two of these models, basically. This one here is pretty nice for that one operation of are they neighbors? It's really fast. Can you think of anything that it's a little slower at than some of the other representations or not as good for? Yes?
Possibly printing out the graph.
Printing, yeah, I mean, it might not be an operation that would occur to some of you off the top of your head, but just like, hey, print the graph. I guess my vertexes are 1 through 7, so I can print them, but then I have to walk this n squared type of thing, v squared type of thing to answer very much else. Yeah, to loop and get all the edges takes a while similarly, right? That's kind of slow, kind of bad. What about if I just ask for, give me all the neighbors of vertex 5? How do you figure that out? Yeah?
Like I would never do a vertices after each one is so one.
Yeah, just like walk across that row and look for all the ones and say, here, all the ones that have ones next to them, those are the neighbors of vertex 5, right? In order to do that, you have to loop across here. And how long does that take? Big O of what? N, or I would say V, like however many vertexes you have, that's how many columns you have, right, by definition here. So it takes big O of V to answer how many neighbors there are, or what the neighbors are. With this thing, the neighbors are all smushed in a tight list. So like if there was 1,000 vertexes and 3 of them are my neighbors, I only have to look at this list of length 3 to answer that question. Back on the matrix one, I have to loop over all 1,000 of them to answer the same question. So it's a little slower for that. The other thing is like the memory usage of this. If you have an array, a 2D array of this size, the memory consumption of this is like v squared, right? V times the size of an int or whatever thing is in this bucket here. And so v squared is not the end of the world, but if v is big, then v squared is bigger than that, right? So that could be an issue potentially. So I just wanted to show you that those are 3 ways of implementing a graph, just in the same way that an array and a linked list are both ways of implementing a list or a vector, right? Those implement the same operations as each other. And the goal isn't to say, oh, here's the best one and here's the worst one or whatever. They both had pros and cons relative to each other, right? And similarly here, all 3 of these representations are good at certain things. And which one makes the most sense depends a little bit on what you want your graph to do efficiently. And so the designers of the basic graph library said, well, we're going to use this for assignment 7. So we're going to do a lot of algorithms where you say for each neighbor of V, do this. And so we want our representation to be able to spit out all the neighbors of a vertex pretty fast. And so this is basically what's inside of basic graph. But as you pointed out, maybe if you tweak exactly what kind of structure this thing is, maybe it makes the structure here a little quicker for some of the other queries, which gets you most of the benefit of adjacency list and adjacency matrix at the same time. When you actually sit down to implement this thing, you start discovering that there are a few other issues that come up, like what if it's a weighted graph? What if it's a directed graph? And I think you'll find that all the representations still work. You just have to think about it for a second. How do you do weights? Well, in the matrix, instead of just writing a 1 or a 0, put a 6 or a 5 if the weight is 6 or 5, right? That works. For a directed graph, it just removes the symmetry from the graph. Just because there's an edge from 2 to 3 doesn't mean there's an edge from 3 to 2. Now it's asymmetrical. But that still works. That's fine. And here in the adjacency list, you just store, hey, my neighbor is 5, and the edge it reaches him has a weight of 1 or whatever. Like that's you can handle all these things with all these representations. You just have to think about it as you go along. I've got a grid here of like how long different things take to run. And so I put in red the ones that are kind of slow, and in green the ones that are really fast. I didn't talk about things like adding a vertex or an edge to a graph that already exists. If you already have a nice 2-dimensional grid and you have to add one more vertex, it takes a while to like resize that thing sometimes, so that can be kind of slow. But anyway, they all have pros and cons, things that they're good at, things that they're bad at. One thing I wanted to point out, like in my pictures, let me go back for a second. In my pictures, I said, well, we have vertex 1, 2, 3, 4, 5, 6, 7, and whatever. But I think there's kind of an assumption there that like somehow the vertexes all have numbers, and that it's really easy to say, oh, I'm looking at vertex 5 right now, so I'll jump here. But usually vertexes have names on them, like strings or something, right? So how does a string turn into this? Like, how do you make a 2D grid if they don't actually have numbers associated with them? That's a reasonable question. And what you end up doing is that really you end up using maps instead. I draw a lot of arrays and vectors and stuff here, but really you end up saying, well, the vertex's key is this, and then I'll store this associated with it. So if you're curious and you're bored over the long weekend, here's what I recommend that you do. Look at the basic graph source code, and you'll find there's a lot of like maps from vertexes to other vertexes or something like that. Or you might have a map of vertexes to a vector of edges, which are all the neighbors. That would be like an adjacency list. And a map from vertex to a set of edges, this kind of stuff would be an adjacency list. An adjacency matrix would be something like a double-nested map of vertexes to edges or to weights or whatever that connect them, rather than literally making a 2D array or a vector or something like that.